This video is about control unit and in particular the instruction code. An instruction code is a group of bits that instruct the computer to perform a specific operation. We'll see a basic but very explanatory set of instructions and we'll see the logic circuits needed to fetch, decode and execute instructions. So, if you are ready, let's get started. Our example is taken from the fantastic But How Do It Know by J. Clark Scott. In previous videos, we have seen that all the CPU does is execute instructions taken from the RAM. It is always the same process which repeats itself over and over. In other words, it is a cycle. It is called fetch-decode-execute cycle. In this video we focus on the instruction loaded in the instruction register. We'll see how every bit has a meaning and the logic needed to decode the instruction. First, we remember that the program to be executed is loaded in the RAM memory. And the first thing to do is to fetch instruction from the memory in the instruction register. The address of the next instruction is loaded in the instruction address register, and it has to be incremented by 1 in every instruction cycle, in order to point always the next instruction. Once decoded the instruction and sent the right opcode to the ALU, we load the content of a register in TMP, being it the first operand, and the content of the other register directly in input A of the ALU, being it the second operand. The result is put in the ACC or the accumulator register. Remember, in order to put a byte on the bus, we send a enable pulse, and in order to acquire a byte from the bus, we send a set pulse to a register. As we said, an instruction code is a group of bits that instruct the computer to perform a specific operation. We have already built some important components of Scott's CPU, the RAM memory, the ALU, and we are building the control unit. We have a clock and a stepper in order to synchronize our operation. Now we need a set of instructions and the logic to decode them, thus sending the right signals to the ALU and the RAM memory. This particular group of bits in the screen has a meaning in the Scott's CPU. The first bit is called ALU instruction. If it is 1, the instruction is an ALU instruction. If it is 0, the instruction doesn't involve the ALU. The following 3 bits define what kind of instruction we have to execute. In our case, what kind of ALU instructions. Remember, these 3 bits go unchanged to the ALU and they are called the opcode because they define the operations to be executed. These 2 bits define the first register involved, register A, so the first operand of the ALU. These other 2 bits define the other operand of the ALU, or register B. Both register A and register B are composed by the same 4 registers, R0 to R3. Our instruction states to add R0 to R1 and put the result in R1, or more generally to add RA to RB and put the result in RB. This way is more readable and understandable to a human being, in respect of reading 1s and 0s. If we change the opcode in 10010001, it means shift R0 right and put the result in R1, or more generally, shift RA right and put the result in RB. As you can see, we can have 8 different ALU instructions, 2 to the power of 3. So we can write 8 different ALU instructions in our new language, because this is nothing more than a very low-level computer language. When we add more instructions, we could write a little program in this new language. Of course, in order to execute the program, the CPU needs the bit representation loaded in the RAM, and with a little software called compiler, we can translate our more human language in the machine language with zeros and ones, which can be executed from the CPU. So our instruction can be divided in two parts. The first part is called opcode and the second one address code, because generally define the RAM or register address in which you can find the operands. In our case, we select one of our 4 registers. In order to control the 4 register, we have to act in the enable input to put the byte on the bus and in the set input to acquire the byte from the bus. Let's see how to control the set and enable of our 4 registers. Since our general instruction take the form of do some operation with RA and RB and put the result in RB, we need to act on the enable of both RA and RB and on the set of RB only, because the result is stored only in RB. Of course, RA and RB are composed by R0, R1, R2 and R3, so at the end we have to act on the set and enable of R0, 1, 2 and 3. Let's see how. First we choose the right register with the decoder's bits 3 and 2 for the register A and bits 1 and 0 for register B. Once chosen the register through the bits 0, 1, 2, 3 of instruction register, we need the AND and the OR because they allow the enable and set only in the right time. So for example, when clock E is up and when reg A is up. For example, if bits 3 and 2 of the instruction registers are 0, 0 when the first decoder output is up, and when reg A is up and clock E is up, we send the up signal to the enable of register R0, putting R0 content on the bus. Now we come back to our stepper, which provides us the sequence of pulses in which we can perform the operations. We consider 6 steps, being the 7th used as a reset and restart of the cycle. The 6 steps cycle is our instruction cycle. It lasts 6 clock cycles, and we'll see in these 6 steps we fetch, decode and execute our instructions. So we do a lot of micro operations in order to execute our instructions. Once we saw how to control the register through bits 0, 1, 2 and 3 of the instruction register, we can see how to use bits 4, 5 and 6 and 7 to perform the ALU instruction. First, remember bit 7 is the ALU instruction bit. If it is 0, it is not an ALU instruction, so it blocks the 3 and the AND in step 4 and in step 5, thus avoiding to use set and enable of reg B and TMP. If bit 7 is 1, we have an ALU instruction. In this case, the 3 and let pass the bits 4, 5 and 6 unchanged, because these bits are the opcode. This happens in the right step, which is step 5. This part instead is used to avoid the storing of any byte in reg B when there is a compare instruction which has a opcode 111, so bits 4, 5 and 6 all to 1. Now let's see the execution of the ALU instruction step by step. We start with bit 7 up because we have an ALU instruction and with some code in bit 6, 5 and 4, which define the kind of ALU operation. As we saw in previous videos, with enable pulse we put the byte on the bus and with set pulse we acquire it in a register. When step 4 is up, we give an enable pulse to reg B, putting its content on the bus, and we give a set pulse to TMP, acquiring the content of the bus, so the content of reg B. When step 5 arrives, we send the opcode to the ALU and an enable pulse to reg A to put its byte on the bus. In this situation, we have the opcode selected, the first operand reg B in the TMP register and the second operand reg A in the bus, so the ALU, being a combinational circuit, immediately performs the operation and we acquire the result, giving a set pulse to the accumulator register. When step 6 arrives, we give an enable pulse to the accumulator register and a set pulse to reg B in order to store the result of the ALU operation in reg B. So we have seen how our control unit decodes and controls the ALU instruction. Fetching the instruction in the instruction register, we start the decode phase and we have a logic for controlling the registers and another logic circuit for controlling the opcode and the execution of an ALU operation. We use all the bits of our instruction, but only steps 4, 5 and 6 of the stepper. We have seen so far only the decoding and the executing part. Of course, in step 1, 2 and 3 we perform the fetch part, in which we put the instruction from the RAM in the instruction register and we increment by 1 the instruction address register. Let's see it in detail. In step 1 we do two things. First, we put a 1 as first operand of the ALU, putting in up bus 1. We give an enable pulse to IAR, putting the instruction address on the bus, and we give a set pulse to MIR to acquire the instruction address. MIR is memory address register. In this way, we open the RAM cell in which there is the instruction. Simultaneously, we have a 1 in the first operand of the ALU and the instruction address register content in the bus as second operand of the ALU. Since the opcode lines are 000 by default, the ALU performs an add operation, adding 1 to the address instruction, thus obtaining the next instruction address. So we give a set pulse to accumulator register in order to store the result of the operation. In the second step, we give an enable pulse to RAM, which put the instruction on the bus, and we give a set pulse to AR to acquire the instruction to be decoded. The last thing to do is storing the incremented address in the IAR or instruction address register. For doing this, we send in step 3 an enable pulse to accumulator and a set pulse to IAR. As you saw, we have incremented IAR and fetched the instruction in the instruction register. Of course, the fetch part is always performed in the first 3 steps, because in the following 3 steps we have the decoding and executing part, no matter for the kind of instruction we have. Thank you for watching. Please leave me a comment and let me know if you liked this video. Make sure you put the thumb up, click the notification bell and subscribe to my channel.